Quantum mechanics is one of the most profound and successful theories in the history of science, providing a fundamental description of the physical properties at the scale of atoms and subatomic particles. Developed in the early 20th century, it revolutionized our understanding of nature, introducing concepts that challenged classical intuition. This article delves into the principles of quantum mechanics, provides examples to illustrate its concepts, and draws conclusions on its significance and implications. Particles such as electrons exhibit both particle-like and wave-like properties. This duality means that particles can display interference patterns like waves, but also can be counted and detected as discrete entities. Physical quantities such as energy, momentum, and angular momentum are quantized, meaning they can only take on discrete values. For example, an electron in an atom can only occupy certain energy levels. Formulated by Werner Heisenberg, the uncertainty principle states that it is impossible to simultaneously know the exact position and momentum of a particle. The more precisely one quantity is known, the less precisely the other one can be known. A quantum system can exist in multiple states at once until it is measured. This principle is famously illustrated by the thought experiment of Schrödinger's cat, which can be in a superposition of being both alive and dead until observed. When particles become entangled, the state of one particle is directly related to the state of another. No matter how far apart they are, changes to one particle's state will instantly affect the other, a phenomenon that Einstein referred to as spooky action at a distance. The state of a quantum system is described by a wave function which contains all the information about the system. The square of the wave function gives the probability density of finding a particle in a particular position. Some examples of quantum mechanics, like the double slit experiment. When particles such as electrons or photons pass through two slits and are not observed, they produce an interference pattern on a screen indicative of wave-like behavior. However, if they are observed going through the slits, the interference pattern disappears and they behave like particles. Particles can pass through energy barriers that they classically should not be able to surmount. This is essential for the operation of many electronic devices, such as tunnel diodes and nuclear fusion that powers the sun. The discrete energy levels of electrons in atoms lead to the emission or absorption of light at specific wavelengths, creating atomic spectra. The quantization explains why elements have unique spectral lines which are used in spectroscopy to identify substances. Quantum computers utilize qubits, which can exist in superpositions of states. This allows them to perform certain types of calculations much faster than classical computers. For example, Shor's algorithm can factor large numbers exponentially faster than the best-known classical algorithms. Quantum mechanics has far-reaching implications for both fundamental science and practical technology. Fundamental understanding. It provides a deep understanding of the micro-world, explaining phenomena that classical physics cannot. It underpins much of the modern physics, including quantum field theory and the standard model of particle physics. Quantum mechanics is the foundation of numerous technologies, including semiconductors, lasers, magnetic resonance imaging, MRIs, and the quantum computing. These technologies have revolutionized industries from computing to medicine. The principles of quantum mechanics challenge classical notions of reality, determinism, and locality. The observer effect and the role of probability in fundamental processes provoke ongoing philosophical debate about the nature of reality and the limits of human knowledge. Quantum mechanics continues to drive cutting-edge research. Quantum entanglement is being explored for secure communications, quantum cryptography, and quantum states are being harnessed for high-precision measurements in quantum metrology. Quantum technologies hold promise for solving complex problems in chemistry, material science, and optimization. Quantum simulators could model molecular interactions with unprecedented accuracy, potentially leading to breakthroughs in drug discovery and materials design. In conclusion, quantum mechanics is a cornerstone of modern science, profoundly altering our understanding of the universe. Its principles, though often counterintuitive, have been confirmed by countless experiments and have paved the way for groundbreaking technological advances. As research continues, quantum mechanics will undoubtedly lead to new discoveries and innovations, further expanding our comprehension of the natural world.